In this video, we're going to talk about the rate determining step. And this is quite a hard one to get hold of. But be aware that when it comes into exams, there's only a certain amount of questions on this because there aren't that many different examples. And we'll go through almost every single one through the worksheet and through this video. So what is the rate determining step? Now, every single reaction has a series of steps. You'll see that from when you have an energy or enthalpy profile where it goes up and then comes down like this. Now, that means normally what you do is you go from the reactants to an intermediate and then down to your products. So we have to create these series of steps when we do a question in an exam. Okay. Now, the slowest step is the obstacle for the whole reaction. Okay, so that stops everything and slows everything down because everything's based on that slowest step. And the overall reaction can be no faster than that slowest step. So the slowest step is called the rate determining step because it determines the rate overall. And I'll refer to it sometimes as the RDS, as in the rate determining step. Now in green here, you can see the slowest step is the rate determining step because one of the questions you get in exams is, can you define the rate determining step? And all you need to say is it is the slowest step, the one with the lowest rate. Now, we'll put that up there and then give you an idea of what this is. So you've got a picture here of people making a cake. Have you imagined this lady here? Okay, she is putting on all the cream and she's putting on all of the strawberries. Okay, and then the lady here, okay, she is then going to finish the decoration on the cake. Well, she can't do her job any faster compared to what she can do. So she has to wait for the lady in white to do her job first. And if the lady in white is taking the slowest time, she would be the rate determining step. Okay, or the lowest, or the highest amount of time, I should say. So what does this mean in terms of chemistry? So here we have a reaction, and you usually will be given a reaction, okay, and then you'll be given the rate equation. Now, we're first going to go on what does the rate equation mean. So the rate equation means here you've got two reactants, you've got the CO here, or the carbon monoxide, and you've got the NO2. You can see the NO2 is only in the rate equation, and you can see that it's been raised to this order 2. So what that actually means is that the NO2 is a second order reactant and the CO is a zero order reactant because the CO doesn't appear in the overall rate equation. That means it's not affecting the overall rate in any way. If we move this up and then we go through some of these rules to create these rate determining steps in these equations for the mechanism, it's usually followed by further faster steps. Not always, sometimes it will be the second step, but we'll talk about that later. The sum of all the steps that you make must add up to this overall equation that you're given. So it must add up, and we'll talk you through how to do that now. Move that to the side, okay? And then look at the most common one, which is a two-step mechanism. Now, first rule, the orders in the rate equation tell you what molecules and how many of them are in the rate determining step. Now, we know from this one that we've got NO2 and it's raised to this order 2. That means, according to this rule right here, that there are 2 molecules of NO2 in the rate determining step. So let's move that over to the side, okay, and then let's start doing our mechanism. So first of all, we're going to do a 2-step. So we're just going to literally do, and I would recommend you do this most of the time, just put your 2 arrows ready to start. Then from this point, you go up to the rate equation. You can see it's NO2 squared, or NO2 to the 2. That means, according to that rule down there, that there are 2 molecules of NO2 in the rate determining step. So the rate determining step is usually the first one. So if they refer to the first one as the slowest step, they're telling you it's the rate determining step. So I'm just going to label this as the RDS, our rate determining step, going across the top. Okay, and they normally give you 2 lines for your 2 equations as well. The most difficult ones include more than that, but for this video, we're just going to talk through the 2 steps to start off with. Now, if that's the case, we know from that rate equation that there are there is NO2, okay, and there are 2 molecules of that in our rate equation, or our rate determining step, and the rate equation. So we then go across and then we start to look, well, these 2 steps must add up to this step up here. Now, we know there's only 2 NO2 in the reactants. There's 2 NO2. That means there's no carbon in the first reaction, in this 2-step mechanism. There's no carbon whatsoever, but there is carbon up here, which means that down here must be the molecule of carbon, because to make, one of the rules are, you sum up all the steps, it adds up to the overall. So if there's no CO2 in the top one, because that can only have 2 molecules of NO2, the CO must be in the one underneath. So we've got both of those. Now you know from this that there's only nitrogen and oxygen in the RDS, which means there's also no carbon dioxide. So therefore I can go and I can put carbon dioxide in my second step. So you see it's a bit like a puzzle. Now from that point, you then have to think a little bit harder. So we've got NO here, okay, and we haven't got any nitrogen that we can see down here for the starters. Okay, so it makes sense that this NO is at the top. Now if we put the NO there, this is where you have to be imaginative, okay? So you have to be really imaginative. What's really important is that rate determining steps have to balance with atoms and have to balance with charge, okay? And we'll show you another example of charge later on. But they have to balance with atoms and they have to balance with charge. At the moment, this balances with charge because it's neutral, and that's neutral. Okay, so the second rule that we need to start thinking about is intermediates. So intermediates are the thing that you use up, okay, you make, and then you use up. So I make here, so this would have my intermediate, and then to get rid of my intermediate, because my intermediate doesn't appear in the overall equation, so it won't appear in this overall equation, I have to make something up here and then use it up here so that it disappears and cancels. Okay, and every single rate determining step will have intermediates. So you've got to look, this is one of the major steps, you've got to look for that intermediate. So if I look here, I know I've got NO. Okay, what is left from 2NO2 from NO? Well, there are 2 nitrogens and there are 3 oxygens remaining. So you can just make things up. You can literally just make things up. It doesn't have to be absolutely perfect. It just has to balance with charges and balance with atoms, okay? So you don't have to, for example, know that that is a radical. It is a radical, but you don't have to know. You can just put NO3. You can just say, right, what's left over from NO? NO3. Well, I'll just put NO3 there, okay? Now, if NO3 is there and it doesn't appear in the overall equation, NO3 has got to come down here. Okay, so we've got our NO3. So that means our NO3 is made and then used up, which means essentially it cancels when we're making it into the overall equation up here. So if we carry on, we think we've got our RDS sorted. Then we have to look at what happens here. Okay, so what happens here? Now, here's the really clever thing. In the equation itself, there's 1 NO2, but in your RDS, there's 2 NO2. So I've got too many NO2s. So it makes sense that I need to get rid of one, and that cancels. And you can either cancel it because it's used up, then regenerate it, or you can cancel it because it is made and then it is used up. So one or the other. So here, I have used it up, and here I'm going to generate it. So remaining, what's remaining here, if 1 oxygen goes onto that carbon monoxide, okay, I can make NO2. Now, if that's the case, that all balances, so checking it all balances, that all balances, it balances charge-wise because there's no charges anywhere. And now we can just check, does it fit the overall equation at the top? So does it fit the overall equation at the top? First of all, the intermediate cancels. Okay, so it cancels, so it doesn't appear in the top. The other thing is, our NO2, one of our NO2s cancels. That means basically what you've got is NO2 plus CO goes to NO plus CO2. And that is how you do a rate determining step question when you've got a simple two-step mechanism. So now it's good to go over the general rules again and for you to write them down if you need to, okay? So the orders in the rate equation tell you what molecules are in the rate determining step and how many there are. Just look at those orders and it tells you how many. An intermediary will be made, which must be used up in the next step. And that can be anything you want. If you find out that there's enough atoms left of one, so you say I have 1 nitrogen and 2 oxygen, just call it NO2. You don't have to worry about whether it is a thing or anything like that, just use them up. Now, the atoms and the charges must be balanced. And we'll talk about another example where you use charges in a minute. The other step will also include the other species in the overall equation. Okay, so they're in the overall equation, which have not been used already. So basically, if you're doing step 1, you've taken out your rate determining step molecules, well then you have to put the other molecules usually in step 2. The mechanism is consistent with the overall equation. So that's the last check you should do on any of these, is check that the mechanism cancels and everything cancels down, leaving you behind what is in the overall mechanism. So let's look at an example here, and I'd like you to stop the video and do this example, okay? So first of all, we've got a rate equation here. The rate equation has a chlorine radical and ozone. That means they're both to order 1, first order, so therefore there's 1 molecule of each. You see there's 1 molecule of each here. Next thing is, it makes sense, because you've got O3 here, and you make O2, the overall is O2, you make 1 O2 here. Why does that make sense? Well, it does because you've got 3 oxygens. Now, if you do that right now and you've made 1 O2, you can't make 2 O2 because there's only 3 oxygens. You're limited. You've only got 3 oxygens. That leaves behind 1 oxygen and the chlorine. So what we do is just put them together. So if you look here, put them together, and now you've got this intermediary. Okay, now you must use that up in the next one. So you see here using it up in the next one. Now from that point, now you can look down and go, right, okay, I've used up my O3, I haven't used up my O radical, so let's add the O radical. Now if that is the case, and we'll go through all of this now, if that is the case, you need to make another O2. There's your other O2. And if you take the O2 off here, you leave behind the Cl radical. Now, really, really important. Okay, you have a Cl radical and a Cl radical here, which means that Cl radical is used up and that's regenerated. Now, if that's used up and that's regenerated, that means it's a catalyst. Okay, now, also the ClO cancels with the ClO. So if you look at it here, the stuff that isn't coloured, the molecules that aren't coloured, are the ones that don't cancel. So you've got O3 plus O dot, O3 plus O dot, and 2 O2s. So the suggested mechanism is consistent with the overall equation, and everything is balanced charge related. They're not too worried about you putting the radical dots on, by the way, so don't worry if the radical dots are there. They usually give you the mark anyway. But again, let's just show this cancelling. So you've got the cancelling of that, which means that is a catalyst because it's used up and regenerated, and then your intermediary cancels as well. And that goes on to our exam tip. Okay, if they're used up and regenerated, then it's a catalyst. And that is your definition, especially in your second year of A-levels, for a catalyst. Used up, then regenerated. So why is something a catalyst? Because it's used up and it's regenerated. Now, let's go to our next example. And again, stop the video, try and do it yourself. Okay, there are 2 ways of doing this. Okay, so see if you can come up with both ways. Now, if you look at this, S2O32 minus, S2O32 minus. So it's 1 molecule of this, 1 molecule in the RDS, because this is the first order. We can then look down and say, right, there's 2 H plus here. Well, there's no H plus in the first equation, no H at all, so the H plus must be in the second one. So there's your H plus. So we've got our reactants right here. This is where it gets a little bit difficult and can be a little bit difficult, but we'll show you one way of doing it first. You need to use your current knowledge, okay, to have a go at what this intermediary is. Right. Now here's the important thing. It is 2 minus on this side. So it's 2 minus. And you can't change the reactants because the reactants are in the RDS, the rate determining step, and they're indicated by the rate equation. So I can't change how many of these I have. So I have to think of how can I make 2 minus on this side? Is there any ions that I know that are 2 minus that include sulfur? So the one you can think of is SO3 2 minus, hopefully. Okay, so SO3 2 minus. You can't do SO4 2 minus, which is sulfate, because there's not enough oxygens, but you can do SO3 2 minus. Now, if that is the case, that leaves behind a sulfur because you've taken away SO3 2 minus and you leave behind a sulfur. So that then starts to work out because your sulfur is down here. Your SO3 though must be, because it doesn't appear in the overall equation, an intermediary. And so we've done our intermediary there, okay, or intermediate here. Now if that is the case, we still haven't made our H2O and we still haven't made our sulfur dioxide. So if you look here, that's where the sulfur dioxide and that's where the H2O, and it does balance. You can see this is 2H plus, add 2 minus, that is neutral, and this is neutral. Okay, and it's all just about what is down here, and therefore I can guess what is up here. And that is your first way of doing it. There is another way of doing it, which please try, okay, but I will show you that straight away. So think of it like this. Now you can see that there is this thiosulfate here, this S2O3. I know it's got to be 2 minus. What is the other thing I can think of that's 2 minus? Well, there's oxygen in there. I can think of oxygen as 2 minus. Then that makes sense because I've only used 1 oxygen. I've got 2 sulfurs and 2 oxygens left over. Well, that makes sense. I can make SO2, which is down here, and S, which is down here. I know that the oxygen is the intermediary, and I know the H plus comes up here because it's not in the rate determining step. And 2H plus plus O2 minus is H2O. And again, this cancels out and will create your overall equation. So that is your 2 methods of doing this one. But just want to emphasize that sometimes there are more than one way of doing it. So on MART schemes, it normally says allow any sensible or any correct mechanism. It doesn't always list all of them because there can be many ways of doing it. But this is the 2 ways of doing this rate determining step question.